Morning. Okay, so today I was flip-flopping back and forth. I don't know how I want to tackle this. I did give you videos for chapter 5 on clustering, so that's fine, and I was tempted to finish it, but I think it's more important that we start chapter 6. And so chapter 6 is on, where is it? Statistical inference, which is kind of a big part of, well, any analyses that you do. And so I just want to introduce inference today, and then we're going to spend quite a bit of time here in chapter 6, kind of learning the ins and outs of inference. And so chapter 6, is on statistical inference. Because you guys, I'm thinking about the wet crew. You're not part of the crew that's taken 121 already, right? Stat 121? No? Because I think this one is instead of that. So then it's very important. Okay. So let's start. Let's take it from the top. What is, let's talk about what inference. What is inference? Inference is when we use sample information to learn about the population, which should sound familiar because that's what we said. Okay, well, if we're talking about statistics in general, then we're taking sample information to learn about the population. And so statistics is generally inference. There are other things that we can do, but generally it's what we're doing. It's what's for dinner. Can't remember what ad that was. Ad. Is it? Yeah. Funny. I feel like I say it all the time, but I don't know what it's from. So it's when we take sample information to learn about the population. Okay. There are kind of two different paths that we can take. And if we take it all the way back to just general variables, right? If we have a variable, which is kind of where we started at the beginning of the term, and we said, okay, all variables, so any column in a data set can be classified as either categorical or numerical. I think this textbook uses quantitative and categorical, which to me feels like a weird mashup. So, but whatever you prefer, categorical or qualitative. Oops, if I can, qualitative, I don't know. And then I'll scoot this over, make room for myself, versus numerical or quantitative. So what we're going to be doing, right, if we're taking sample information to learn about the population, really what we're doing is we're analyzing these variables, right? And so to analyze, and maybe I'll put that that word here, right? So analyzing a variable is our kind of our overarching goal. So to analyze a categorical variable, if we think about a categorical variable, I have a column full of what category some observation is in, right? What color car do you have? Red car, black car, white car, red car, right? And then how do we summarize that? We can summarize that usually in a table or a bar chart or something like that, because we have counts, right? So we have counts in each category. And so those counts, how we analyze those counts. So we analyze counts. Oops. And we turn those counts into proportions. Potentially more than one. So usually what we do is, oh boy, I have so much to say and no voice to say it. So what can we do? We can start by taking one proportion. Is it, are we interested in, is it more than 50%? Is it less than 50%? Right, we can compare one proportion to just a number. Then we can level up and we can say, well, what if I have two samples of proportions, right? Is the proportion of black cars significantly different from the proportion of red cars, right? That kind of thing. So now I'm comparing two proportions. And then we can level up again and we can say, well, what if I have more than three proportions that I want to compare? How do they compare to each other? And then we can move, and then past there, we do the same thing over and over again. And so we're analyzing these proportions. Whereas for numerical data, so thinking back to what a numerical variable is, right, it's going to be some measurement, right, and some, distance or height or something like that. And so then we're going to analyze measurements. So what we're going to do to summarize those measurements is we analyze the mean, right? The means are the averages. Okay. So then again, we can start by saying, okay, well, is the mean height significantly different from 160 centimeters of students at Okanagan College, for example? Right, so we have one mean and I want to compare it to just one number. Then we can say, well, okay, what if I have two sample means, right? Is the mean height of, let's go with something silly, the mean height of females significantly different from the mean height of males, right? Then we're comparing those two means to each other. And then we can take it one step further and say, well, what if I have more than three or more means? How do they compare to each other? And so we follow that same structure kind of always. So there's an example in the textbook that I wanted to steal that I had scrolled to and then I managed to skip it. It's not too far though. So because I'm old and set in my ways, or maybe not old, but I am set in my ways of teaching this stuff and approaching it. I'm going to stray a little bit from the textbook just because I don't really love how they approach it. I find that it can be confusing. And so I do want to go through these problems in the order that I introduced them as we went through. So one sample proportion, two sample proportion, three or more, and then move into means, which they don't do. They do one sample proportion, one sample mean, two sample proportion, two sample mean, and it gets kind of boggy. And so what we're going to be talking a lot about is what type of question it is. Now, for this example here, I just want you to think about, is this a proportion question? So am I going to be analyzing a proportion, or is it a means question where I'm going to be analyzing the mean? I can't lose my voice, although it's like the only ailment I haven't had, so I guess that's typical. And so here I want you to read through these. Proportion or mean. I'll do an example here. And I'll bring it up and kind of make it as big as I can here. Just think about. I would read it to you, but no thanks. So for this first one, and there are always clues, proportion, yeah. Mostly because it says the proportion of registered voters, right? And so the word is typically in there, or you kind of end up saying it regardless. But that's not always obvious, right? When you're first starting out and reading these problems, do I have a mean or do I have a proportion? And so even I think this last sentence kind of gives it away. So even without it, though, you would have a count, right, of those voters who indicate a preference for the candidate, and you've got a total, right? And so that tells you that it's categorical, and you've got these counts, which you can turn into a proportion. In fact, the proportion here is going to be 160 over 400, just 0.4. Okay.
Isn't it numerical?
So they are counts, but because they're counts, they're coming from categories, right? So we have counts in the categories. And so if you think about how the data set would be organized, right? You would have a column of, do you favor this candidate? And the answers would be yes or no, right? Would you vote for this guy? Yes or no? Or woman, I guess. Wow. Emily. Anyways, would you vote for this kid? No. Right, so your responses would be yes, no, yes, no, yes, no. So then if we think about the next one, I'll give you some time to read it. Nice. So now, what are we trying to measure? Well, we do have the mean useful life of the new tires, right? So again, so now it's kind of in there leading you down this path. And so we've got a sample size of 120 tires that we're looking at that we've tested. And then we're given a sample mean of 36,500 miles. Feels like a lot, right? For tires. I don't know. How many kilometers would that be? For a set of tires? Whoa. Oh. Yeah, I don't. I'm on winters till June.
Yeah.
Just because I can't get my act together. One day I'll get it sorted. Yeah, so maybe that's my problem. Okay, so then if we think about how this column of data would be set up, right, what would it look like? You would have how long each tire took for its useful life, right? And then we've got 120 of those tires, and then the average of all those is 36,500 miles. Okay. Now, we're not going to explore it here, but what could we do? We could compare this to just some number, right? Is this, and I'm going to be saying significantly quite a bit, and that's kind of why we're we're doing statistical inference is to be able to say that, well, this is significantly more than 35,000, right? For example, it is more than 35,000, but is it significantly more than 35,000, right? And so those are the tools that we're gonna develop, right? And so we don't have the spread here, right? But it depends on the spread, right? For example, if you think about, because everything hinges on the spread, if you think about mosquitoes, right? Then how big is a mosquito? It's, I don't know, like this. I think we can all agree they're like this generally, and there's very little spread there, right? So if I told you that, oh, I found a mosquito that's 1 centimeter longer than the average, you would say, oh, hold up, that's crazy. We need to report that, right? Why? Because the spread is so little, right? You're expecting such little variation in your mosquito sizes, right? Whereas if I said, okay, now let's think about the average, we'll talk about the length of a dog, right? You're expecting, well, there's lots of different kinds of dogs, right? There's lots of variability. There's lots of spread in these lengths of the dogs. And I say, oh, I found a dog that's 1 centimeter longer than the average dog. You'd say, oh, that's cool. That's not impressive. And so 1 centimeter in both scenarios, it all comes down to the spread, right? And so we don't have the spread here, so we can't determine it, but we would, right? If we had this column of data, we could find the standard deviation, which would be our spread, and then we can use that to determine, well, is 36,500 significantly different from 35,000, for example, right? Or maybe we have a different brand of tires, right? So now I have a second sample in my data set with that other brand of tires, and I've done the same thing, right? Now I'm interested in comparing those means. Are the mean useful life of the new tires significantly different from each other, right? So not just comparing to a number, but maybe comparing to a different sample. And so those are all things that we'll be able to do. Pretty neat. Okay. So for us, it's going to be really important to first decide, do I have a mean question or do I have a proportion question? Okay. And so, like I said, usually there are clues in the question, right? And especially if you're given a mean, then it's a means question, right? And so that's kind of my clue. Okay. All right. So in terms of inference, we're just kind of introducing all these things today. There are two main things that we can do. Okay. So we have sample information, and we're going to consider our sample information our best guess. So we call it our point estimate. Okay. And so we have the sample information, and we're trying to learn about the population without collecting the entire population, because that's either impossible or very expensive or both usually. And so we're trying to learn about what the population might look like. And so from our sample, we can build a confidence interval. Now, a confidence interval is an interval around your estimate. And if you're reading kind of articles or scientific journals and things like that, then you'll always see confidence intervals. Okay? And we use confidence intervals often without calling them confidence intervals. So if you ask me, Well, let's go kind of, my go-to is how far is it to my house? But let's say, yeah, let's keep it that way. So I live downtown, and so you ask me, hey, how far is it to your place? We all understand that there is an exact distance, right? However we want to measure, we can talk about how we're going to measure it, but there is an exact distance, right? Let's call that the population measurement, right? We're trying to figure out what that is without actually measuring exactly how far it is. I have a pretty good idea, right? And that's the information that I have from my sample. I would say 5 kilometers, right? Let's just kind of guess. And then I would follow it up with, just kind of naturally, I would follow it up with plus or minus, I don't know, half a kilometer, right? That's pretty good, right? And then you would say, or you might not say, but you should say, well, how confident are you? I'd say 95% confident, right? We understand that there is this true measurement, and I'm trying to capture it, right? And so what could I do? If I want to increase my confidence, what could I do? I could
Measure.
We're not measuring because well, it would be very difficult. But what could I do? I could increase my bounds, right? I could say, well, 5 kilometers plus minus 1 kilometer. Then I'd be more confident, right? Plus minus 10 kilometers. Well, that's useless. I'd be 100% confident though, right? And so there's this trade-off between how confident you are and precision, right? Your estimate becomes, or your interval becomes kind of useless at some point if your bounds are too wide. And so what we're doing with this confidence interval is we're trying to take our best guess, right? So our sample information, and then we build bounds around it to try to capture that true distance to my house, or that true population proportion, right? And so it becomes kind of this net. Now, it's really important to remember that the true distance to my house is fixed, right? And so we've decided what route we're going to everything's fixed, right? The population mean, for example, exists, it's fixed. We're never going to know what it is exactly, right? But it's not moving around is the thing. Whereas if I maybe, oh well, my example doesn't really extend this way. So what if we talk about the mean height at the college, just everyone at the college, right? We can talk about the average height of everyone at the college. It exists. We could measure it. We don't want to. We don't need to, right? So it's fixed. What could I do? I could take a random sample around campus, and I could figure out what my best guess is, right? What if I released that random sample and I took a new random sample, right, of the same size of people? You'd expect that average, the sample average, to be similar, right? But not exactly the same. There's going to be variability in that the sample means, right? But then if you're building, so you've got your sample mean here, and then you're building bounds around it, but then it can always kind of move around, right? And then, so that's where, let's say, a 95% confidence interval would come from, is because I'm relying on my sample estimate being close to the population parameter, which is not necessarily the case, usually, but not necessarily. And so a confidence interval is a point estimate from the sample, and a point estimate is my best guess. I'm keeping it generic because the point estimate could be a sample proportion, it could be a sample mean, right? So it can be either of those. And so a point estimate from the sample with the bounds, it's technically called the margin of error, but I haven't called it that yet, so. Oh my gosh, there. With bounds to try to capture the population parameter. Right. So parameter is a measurement from the population, right? And so here, the P and the P a parameter is a measurement from the population. Wait, keep it on one page. Okay. So that's the first thing that we can do, right? We can kind of have our sample information, so our sample mean, we build bounds around it, and there's formulas for that, right? Excel does it, and well, any software does it. And so we can build these confidence intervals, right? The other thing that we can do is hypothesis testing, which is kind of the more formal set of inference, okay? Hypothesis testing. Think back to, I don't know, maybe even grade school, right? You have a hypothesis, and then you test it, and then you see if it worked or not, right? If I boil water, what's going to happen? I hypothesize it's going to turn into a gas. Oh, it did. It's not going to be as fun, obviously, as boiling water, I guess. But we do the same thing, right? I have some hypothesis about how my sample behaves or how my population behaves, right? And so I hypothesize that the mean useful tire or the useful life of the new tires is different from 35,000, for example, right? We have the sample information, which is higher than 35,000, and I want to prove, well, I guess I should say significantly higher. There's a reason I didn't, but that's okay. So I hypothesize, right? And then we can use formulas and statistical inference to determine, well, the probability of that happening is too small. So then I have evidence against my hypothesis, my initial hypothesis. Okay. And so here, hypothesis testing is, let's see here. How can I summarize it as briefly as I can? Using a point estimate, which we just said was the sample information or my best guess, right? My sample proportion or my sample mean. So using a point estimate to test a hypothesis about the population parameter, right? Eventually, I'll stop saying the population part because it's redundant, because a parameter is from a population. But for now, about the population parameter, for now, I'll keep saying it just a little bit longer. There are different ways of doing that. Now, one of the main things that we're relying on here is, okay, so I'm using this point estimate, so the sample information, to try to capture the population parameter, right? Or I'm using this point estimate to test this hypothesis about the parameter, right? Its corresponding parameter. What am I relying on? I'm relying on my sample being representative of my population, right? That's a key kind of assumption. Okay. I don't want to say assume, well, maybe I do. We assume, but we'll talk about how we can assume it. We assume the sample is representative of the population. That's kind of an obvious one, right? But there are ways that we can, I guess, check whether we can assume it or not. Okay, and so at its core, what we need to have a random sample. Okay, and so just want to talk a little bit about. I actually can't remember if we talked about random sampling and how to do it. It's been a while. I'll just do a little recap. Why not? And so how we can random sampling ensures, I guess, yeah, as well, it ensures as well as we can that the sample is representative of the population. So the sample is representative of the population. Yeah. What are some ways that we could do that? So in the textbook, they introduce kind of two different types of random sampling. And so one of them is where you have just a finite list of things that you want to sample from. So you are doing research here at the college and you have a list of students, and they're all the students that we have, and you can randomly sample from this finite list of things. And so let's see here. There's kind of two options. So from a finite population versus an infinite or infinite population. No, it's not infinite, but that's how I remember how to spell it. So we have a finite population or an infinite population. And so here we have a list or some sort of sampling frame. So just imagine you have a list of the entire population. Versus an infinite population would be if it's constantly changing or, you know, it's just impossible to list all the things that you could sample from, okay? And so kind of constantly changing. I feel like it's kind of obvious if it's infinite, right? Then there's no end, right? If I ask you to sample ants, for example, well, yeah, it's finite, all right, but yikes, right? So in theory, infinite, right? The number of ants in the world. You could restrict it to a certain area, right? Then you'd have a finite population to sample from, right? So you can always kind of pare it down. But what are you gonna do? So the easier solution is if you have a finite population, or if you say, I pretend I have a finite population, right? Pare down this area of ants that I want to sample from, right? I've got a group of ants and I'm just sampling from that population. So one way that you can do it is you have your list of ants, I guess, or students. Let's say students. You've got your students enrolled at Okanagan College this year, right? And you want to sample a random sample from this list. Well, what could you do? One of the go-to moves is, there's lots of ways. Go-to move is if you have this list, you can use a random number generator, right? And there's a random number generator built into Excel, for example. It's not very good. It's not very random. There's random.org, which claims to have the most random number generator. I know. Yeah. Because what's a random number generator? Well, someone had to build the algorithm to start at some random point. Well, you can't have it pick a random point because it has no brain. And so you have to tell it where to start, and then it generates kind of random or pseudo-random numbers. But for our purposes, random enough. But we used to have to use, pardon? Oh, yeah. Yeah, I used to use, when I first started teaching, we were still teaching with a table of random digits. So it's just a table. It's, I think, 2 pages long, and it's just random digits. And then, so you have, yeah, let's kick it old school. Let's use a table of random digits. Why not? It's the same concept. So it's just a table of random digits. You take your largest observation that you could have, so your sample size, right? Let's say you have 20,000. No, let's say you have 2,000 in your population, right? Then the length of your digit would have to be four digits. So then you just start at the beginning and you move by 4 digits. And if any of those digits that come up, right, are one of the observations that you could pull, you pull it, right? If you've already pulled it, you can't pull it again, right? And then you move in chunks of 4, right, until you have your desired sample size. Random. A little bit easier than the table of random digits is you use a random number generator to generate a list of random numbers between 1 and n, right, your sample size. And then you attach it to your population, right? Each observation gets a random number. And then you sort by the random numbers and you pick the smallest 30 or whatever your sample size you want to have, right? And so when I worked at a market research firm, we used to have to pick winners for like draws and stuff. Can you please do our survey, please? And then you get a prize. And so to pick those, we had to randomly draw someone, and that's how we would do it, right? First one, if you got one, you won. Cool. So kind of fun. And that's how I was introduced to random.org, because my coworker said, well, it's the most random number generator. I don't know if it still is. That was like 10 years ago. So then we can generate a list of random numbers from 1 to n, right? Lowercase n is your sample size. Attach it to the population, right? The list of observations or the list of elements in your population. Attach it to the population sort, right? And pick, the smallest 30 or the largest 30. Let's say you pick whatever sample size you want. For simplicity, let's say sort and select the smallest 30 for a for a sample size of 30, obviously. For example. So that's kind of fun. There's a sampling function in Excel that you could use, which I haven't looked into the background of what it does, but I'm assuming it does the same thing. Right? It just attaches random numbers without showing you and then pulls out a random sample. So lots of different ways. In any statistical software will do it. Okay? Because we often pull samples. Okay. What if you have an infinite population? Now that's tricky, right? You can't generate a list and attach it and then sort it, right? Because it's infinite, it's constantly changing. So you're thinking about maybe in a production line, you could take a snapshot in time, right? And then you could pare it down to a finite population. But one of the things that you want to keep in mind is to satisfy randomly sampling from an infinite population, you'd have to, sorry, you'd have to make sure that, let's see here, what was the first one that I wanted to say? Oh shoot, I'm drawing a blank. We need to, can't believe I'm saying ensure again, that one, the observations are independent of each other. Are independent. Oops, independent. Oof. What was the other one? It's something obvious that I was like, oh yeah, of course. Anyways, how can you assume that observations are independent of each other? One of the examples in the textbooks is so McDonald's wants to do a survey with people about, how do you like our burgers, whatever, or how do you like our restaurant, blah 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 blah. But the list of customers is infinite, right? They constantly have customers coming and I guess going, right, and buying things. And so one of the ways that they ensured that observations are independent of each other is they said, okay, anytime someone uses a coupon, which presumably would be independent of other customers, right? I have a coupon, I received it, and I go in and I use my coupon, which I guess we don't do anymore, but right. And so if someone used a coupon, then you would survey the following customer, right? So not necessarily the one with the coupon, but the following customer. And the way that they kind of argued that they're independent of each other then is that because people using coupons are independent of each other, right? They're not just coming in slews. And the people following people who have used a coupon are independent of those coupons, right? And so that's kind of a neat idea. I think it's a really elegant solution. Like anything, you can poke holes in it, but it's just generally been considered random enough, right? And so the example is at McDonald's. survey every customer after a customer presents a coupon. Right? Those customers, or you know what, I'm just going to call them coupon customers, arrive independently of each other, right? That's one of the assumptions that we're making. That's one of the things that we can poke holes in, right? I got a coupon, you got a coupon, let's go, right? And so that's not necessarily the case, but it is an assumption that we're making. And so coupon customers are assumed to be independent and customers following coupon are independent of the coupon customers. Of the coupon customers. I'm gonna have to look back and see what that second thing was. It's one of those ridiculous things I can, I know that much. Oh, I knew it. Here it is. I remembered the harder one. Each element selected comes from the same population. Well, no duh. Hopefully, but I guess I should write it down. I'll let myself off the hook for not remembering that one. Oh, I'm on to the next page, kind of annoyingly. Each observation is selected from the same population. Can't tell. Oh, okay. Is this the right time, by the way, before I rely on it? Okay, good. So I can't see the time anywhere. I can talk about this forever. Okay, so selecting your sample, right? As long as you have employed some sort of random sampling technique, right? So whether you have a finite population or an infinite population, right? There are ways of doing that. Now, like you can see, right? Sampling from an infinite population requires a little bit of finesse, right? And also a little bit of arguing. No, it's random because, and they're all independent of each other. And I selected from the same population, and that's that. Okay. So, what's the next thing that we can do? So, I can't remember what week it was, but I assigned the normal distribution, right? And so you worked on the normal distribution, and I'll just say recall the normal distribution looks like this. Well, that's a bad one, but they're always bad for me. Centered on some population mean mu with some standard deviation sigma, so that's our spread, right? And so what could we do with this normal distribution? So the reason it's so useful is that we can use the normal distribution to find areas under the curve, right? Areas under the curve are probabilities, right? The probability of seeing this observation given a population that's centered on mu with a standard deviation of sigma is some value, right? And so the area under the curve is a probability. Probabilities have to be between 0 and 1, right? And so a probability of 0 means there's 0 area under the curve. And a probability of 1 is the entire area under the curve. So the total area under the curve is 1. And so then what we said was, okay, if I have some observation X, let's call it X here, right, on this number line, what can I do? I can standardize this value, right, by calculating a z-score, and I can say, okay, z is x minus mu over, well, sigma for now. Well, z is over sigma, I guess. And then we can use Excel to calculate areas to the left. And then if we need the area to the right, then I can take 1 minus the area to the left, because we treat these all as little puzzle pieces. Okay? So the norm.s.dist function that you learned in Excel, right, is gives the area to the left. So I think let's see here. In Excel, use equals norm.s.dist of z, the z that calculated, right? And then we're always going to have true, because we always want the cumulative area up to that point. Technically, the area at z is 0, right? If you think about area, then the width is 0. So it's going to give you a value, but it's not good. So we always use the true, okay? And so this function gives you the area to the left, okay? And so here, this gives the area to the left of z, right? The z that you calculated. What is z up here? If we think about z, right? It's how far x is from the mean, right? Taking into account the spread. So it's really how many how many standard deviations is x away from the mean. Now you could be below the mean or you could be above the mean, and so that's where the positive and the negative come from, right? But z is a standardized value, and so z is the number of standard deviations x is from mu. Right? How extreme is it? And so then if we have a z-score, right, you can plug it in here and you can find the area to the left, right, but only the left. If we need to find the area to the right, you'd have to leverage the fact that the total area under the curve is 1. And there's old school Z tables, which I would have used in the video, but we don't need those because we have Excel. So kind of grown up from there, but use them if you want to. I can bring you some, but I don't think you need to. So to find the area to the right, right, we find 1 minus the area to the left. So leverage that fact that the total area is 1. Okay. So that's just a little recap. Why do I mention that? Well, we're going to be using this same procedure to find probabilities associated with how our sample or our point estimate compares to our parameter, right? And so here we said, okay, I can standardize how far X is from mu given my spread. Thinking back to the mosquitoes, right? A mosquito that's 1 centimeter larger. Well, considering the spread, that's kind of a big deal. Whereas the dogs at 1 centimeter, a distance of 1 centimeter here with a huge spread, well, that's not going to be a big deal, right? And so we're going to use the normal distribution because of a little thing called the central limit theorem. So the central limit theorem it's an important concept, but it's not really. So when I was taught about the central limit theorem, we just had to memorize it, which is kind of old school, I guess. And so it's one of those things where I'm going to talk about it now and kind of introduce it. But then it's this kind of cool phenomenon that we're just going to be applying, and we're going to make sure that we can apply the central limit theorem. But besides that, we don't really need to kind of think about it too much. But it is a really cool thing. And so what is it? If we think about, let's go back to the heights at the college, right? And so we've taken a random sample of 100 people, let's say, right? And so I have this random sample of 100 people, right? And I measure all their heights, and then I take their average, and all I'm going to keep essentially is that average height. Then I release those students, and I collect a new random sample of 100 students, and I collect all their heights, blah, 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 and I record their average heights. So now I have I'm going to have a list of averages, okay? And so, or a list of point estimates, okay? And so now we, in theory, no, it's because, so we only ever take one sample, right? But here in this theoretical application, we're taking all the possible samples, but it's just to be able to go back and say, when that's why I just need to take this one sample, is because I know the behavior of all the samples in theory. And so that's kind of the mind-boggling part. But so we're just going to use it ultimately, but I want to kind of show you where it came from. And so, not sold.
Just using your example, it's like they're going to get 100 students, their average, and then a second, third batch of 100 students, their average, and so on and so on.
Yeah.
Or we should just get 1,000 students in one go.
So yeah, so that you could, but we want to talk about the behavior of all those samples of size 100, for example. It's going to apply to many different sample sizes, or all the sample sizes, some conditions. But then knowing that, then we can say, okay, then I know the behavior of all samples of size 100. So now if I just have one and I know the behavior of all the other ones, then I can use that to find probabilities, because they will follow a normal distribution. And that's the cool part, and that's the central limit theorem, is that even if you're drawing from a skewed distribution, if you have the collection of all the averages, those averages are going to follow a normal distribution. So that's kind of crazy, I think. So if we, I'll say in theory, because we never would. So if we had a sample of all the possible point estimates, if we had a sample of all the possible point estimates, and not even necessarily all of them, but definitely helpful, or a large sample of point estimates. We would find that they follow a normal distribution. We would find they follow a normal distribution. And what's cool is regardless of the shape of the distribution that they came from. Now, if you're pulling from a very skewed distribution, such as any sort of money situation, right? Income is extremely skewed, right? That kind of thing. So then you need to increase your sample size to be able to even that out, but it does approach a normal distribution. Okay. And so we would find they follow a normal distribution regardless of the shape of the population distribution. So it can be really skewed. And because of the central limit theorem, we're still able to apply the normal distribution for means and for sample proportions, which is even crazier, if you ask me. So you go from categorical data all of a sudden to following a normal distribution. Okay. And so for the Excel exercise on Friday that I'll post, you'll get to try it out for yourself. So I'll give you a population of categorical data, right? Just to emphasize that it works for categorical data as well. And it's what I have made. So you'll have to put up with it. So we've got categorical data. I give you the population, and then I ask you to sample from that population. So then you can find the sample proportion, and you have the population proportion, which we don't usually have, right? And then I give you the data set where I've done it 100 times over, but done the same thing 100 times over. And then so for each of those 100 samples, you're able to calculate the sample proportion. And then all of a sudden you have a sample of sample proportions, just like we said here, right? We have a sample of point estimates, so sample proportions, and then you'll be able to make a histogram of those and they will look normal. I hope. No, they will, because of the central limit theorem. Okay. And then you'll be able to use that normal distribution to find the mean and the standard deviation, right, of this numerical data that you've generated. And then you can find probabilities associated with that. Okay. So just kind of poking around with the central limit theorem. Okay. Now, the central limit theorem, let's see here. I feel like I was going to say something here. I'm not going to write this out every time. We call it the CLT, the central limit theorem. Okay. And so the central limit theorem says that a sample proportion, and so let's start with the sample proportion. So, oh, that's what haha, now I remember. Sorry, guys. I'll just bump this down here. A sample proportion is denoted by p hat, typically. I did notice that the textbook uses p bar, which I don't love, because a bar, to me, I like to be kind of strict about the bar being for an average. Now, it is technically true, but I find that it can be kind of confusing. You're welcome to use whatever notation you'd like, but a sample proportion is denoted by a lowercase p with a hat on it, or if you prefer, p bar. I kind of grew up with p hat, so it's really hard for me to change it. But technically, it is going to be an average of proportions, right? And so that's fine. And this doesn't look like a straight bar, but fix that there. Well, so a sample proportion is denoted by p hat or p bar, and a sample mean, we've seen before, is denoted by x bar typically. So we've got this x bar for the mean, and that's why I find that this is kind of confusing, but it's up to you. Okay, and so what the central limit theorem says with this notation is that, okay, p hat, so the distribution of p hat is going to follow a normal distribution. So any p hat that we draw from, or that we have, we only have one, but in theory, kind of in the clouds, it's being pulled from this distribution of possible p hats, right? And those possible p hats follow a normal distribution centered on p, which is the population proportion. So here, this is the population proportion. With a spread of p times 1 minus p over n square rooted. And so this is the spread, but it's the standard deviation of of sample information. And so we give it a different name. We call it the standard error. The standard error, which is the standard deviation of the p hats. Kind of confusing, but how we write this is the standard error of p hat is the square root of p times 1 minus p over n. The problem that we face, though, is, well, what's p? P is the population proportion, which we don't know. So then we say, okay, how about I sub in my best guess, my p hat, right? And so then in application, since we don't know p, we use p hat, which is our best guess, our point estimate. So in application, we don't know p. So we use p hat, our point estimate. And so now, right, we say it's centered on P, but we don't know P, so we use P hat, which is our best guess for the center. And then we assume that everything's around there and we've got some spread, which we can calculate by P hat times 1 minus P hat. Now, very quickly here, I'm going to move out of calling it 1 minus P hat and just call it Q hat because I'm lazy. Just look at all this writing, it saves me a bracket, a 1 minus another bracket. That's a lot of savings. So I'm just lazy, and it's common. Usually, right? 1 minus P hat is Q hat. And in general, any Q is going to be the 1 minus P version of it. That's just because I'm lazy. And you can be too. So now we know in theory what the distribution of these P hats looks like, right? And so because it follows a normal distribution, I can use Z's to calculate probabilities, right? So here, this means we can use Z to calculate probabilities. And that's the meat and potatoes of the central limit theorem. We also have a central limit theorem for means, right? And so I'll just introduce that here, just so we have it. X bar also follows a normal distribution, and it's centered on the population mean, right? And instead of a spread of sigma, it's a spread of sigma over root n. Now, again, we don't really have sigma because sigma, remember, is the population standard deviation, which is kind of saying, well, at some point I had the population and then I let it go and now I'm trying to figure out what the population looks like. That doesn't really make sense. And so in the same way that we used P hat here, right, we're going to replace our sigma, our population standard deviation, with S, our sample standard deviation, which is my best guess at what the standard deviation might be. So here, the standard error, and I use a little subscript of X bar just to indicate that it's for the sample mean, is technically sigma over root n, but we replace this, we use S, the sample standard deviation, as the point estimate of sigma. So then in application, the standard error of X bar is going to be S over root n. And maybe I'll turn this pink just to emphasize, right, in application. So we have this theoretical, but really when we're applying it, we're going to be using S over root n as our spread, right? And that's why it becomes confusing when we talk about the standard deviation of X bar is the sample standard deviation over root n. And so you're saying standard deviation twice, and that's the reason that we had to develop new terminology where we say, okay, if it's for some statistic, right, so some P hat or some X bar, then we're going to call it a standard error instead. But it is just the spread, and we just calculate it based off of the sample size, or it relies on the sample size. With my last 2 minutes here, looking at this formula, increasing the sample size, right? So increasing n is going to decrease this whole chunk, right? And so because p hat is steady, 1 minus p hat is also steady. I'm dividing by a larger number, which means this general number becomes smaller. If I take a square root of a smaller number, it becomes smaller, right, than it was before. And so by increasing n, we're decreasing the spread, right? And so that's where we get this idea that, which is kind of common knowledge, I think. Well, you want to increase your sample size. You'd have to increase your sample size. Oh, that's a small sample size. You want to increase your sample size. Well, this is the reason you want to increase your sample size, is because intuitively we understand that as we increase our sample size, the spread gets smaller and smaller and smaller, right? And so same thing here. If I increase n, and then I take the square root of a larger number, I get a larger number than I had before, right? You can try it with an n of 100 and an n of 1,000, right? And some arbitrary value of s. But if you divide by a larger number, you get a smaller number. So again, increasing the sample size is going to decrease the spread. And I'll make a note of that here. Increasing the sample size n decreases the standard error of the point estimate, the spread. Okay, and I think that's good. If you have any questions, let me know. Otherwise, I guess I'll see you on Monday.